We're going to move on to our next talk now, which is from Anthony Colaprete from NASA, who's going to tell us about the Volatiles investigating Polar Explorer mission, or VIPER, and the measurements and constraints it'll make. So I'll hand over to Tony. All yours, Tony.
Thank you very much. And I was going to try the clicker, but I'm not feeling lucky. So I'm going to ask to proceed. I didn't move the cats into the other room, though, so we're safe there. So if we could go to my slides. Thank you very much. I'm going to talk about the Volatiles investigating Polar Exploration Rover, or VIPER. It's a lunar water reconnaissance mission, and you'll see why I refer to it as a reconnaissance mission, hopefully, as I give this presentation. Next slide, please. Oh, one back. Oh, go one forward. It seemed to skip through the one on the intro slide. There, stop there. Okay, good. This is a summary slide because I usually go long, and so I've learned to put the summary up front. So I don't need to tell this group that there's been really a revolution in our thinking about water on the moon over the last decade and a half or so. We went from a relatively arid planetary body to one where everywhere you look, you find water, it seems. And we understand that this water comes in a variety of forms, concentrations, distributions, from frost to potentially buried blocks based on radar observations, et cetera. All this said, its nature, its distribution, its origin, these are all questions that still remain very uncertain. And so I think we've seen just in the previous talk and this talk that there's a real need, a desire to get to the surface and really start to make observations at what I call the human scale, the scale at which we operate, if you will, especially from a resource standpoint. That's very important. So this is what's motivated VIPER. It's going to conduct what I call exploration science. So it's really modeled after what we do at the United States Geological Survey in terms of resource mapping, both in processes and techniques. And in a way, it's going to be the first resource mapping mission to another body. We've been confirmed to just last February, a month and a half ago or so, to move into phase C. So we are no longer a concept. We are in implementation. Flight hardware is being built. Our launch right now is November 2023. Next slide, please. This is a quick summary of the various required measurements for VIPER. It is all about mapping the volatiles, and in particular water. One of the things we've done to help organize our operation, our concepts of operation, is to define what we call ice stability regions. And the two figures on the right show models, thermal models like you just saw, of the ice stability depth. So areas that are white are areas that are in permanent shadow, so the ice is stable at the surface. And then as you move away from those PSRs, you can see there's a range of colors from red to blue, which indicate ever increasing depth to which water ice is stable. So those are sunlit regions, yet at some depth between 0 and the surface and 1 meter deep, you will find ice stability, temperatures that allow for ice stability. Doesn't mean there's water there, but it's stable thermally to allow for water. And the figure on the bottom there is what we then do is we map these into 4 different units: dry, deep, shallow, and surface, based on that ice stability depth. So shallow means that ice could potentially be there. Ice or temperatures allow for stability between the surface and 50 centimeters deep. Deep means 50 centimeters to 100. Dry means below, there's no expected stability to at least 1 meter deep. We do this mostly just to help organize our campaign, and also to help map units. And again, this is kind of borrowing off of resource mapping here on Earth. These will go into standard databases that we're going to develop with the USGS to actually build a standardized resource mapping database for use by everybody. So within each of these ISRs, we need to actually measure the total water content to better than 50%. That means that drives aerial density, which is a real big thing for this mission. It's not going to a single location and making a measurement. We need to map, we need to raster, we need to cover area up to 3,800 meters square. So that's a real big effort for this mission in particular. We want to measure down about a half weight percent in terms of concentrations. We need to account for variability and a range of potential variability across scales ranging from 1 meter up to as much as 1,000 meters. We also need to do repeat measurements in multiple ISR types to include, just to try to assess the overall variability between these ISR regions. We need subsurface measurements. That's critical. We have a 1 meter drill as well. And we sampled down in 10 centimeter intervals with that 1 meter drill. And also very important, and we've heard this, this is so true, we need to characterize the environment. We need to be able to provide means to understand, to test hypotheses, to correlate our observations of volatile distribution. So we're going to be measuring isotopes, the geology, surface temperatures, subsurface temperatures, et cetera. Next slide. So that's the whole mission in a nutshell in one slide. This is the integrated rover design. It's a bit boxy, but it is actually a much lower chassis than it looks. It's got 3 panels, solar panels on each side to maximize sun exposure, sun power. It's solar powered. You see approximately a 2 meter mast that does visual stereo navigation. The wheels are actively controlled, meaning they're independent suspension and not a skid steer. So it's a very, very capable mobile platform. Out in front, you see the little kind of nubby thing sticking out the front on the far left. That's the neutron spectrometer that I'll talk about a little bit, sticking out like a hydrogen nose as we drive along. Okay, next slide. Okay, good. So this is the instrument overview. It has 4 primary science instruments. Going from, starting upper left, going clockwise, we have a neutron spectrometer, which will help us map hydrogen down to about 1 meter continuously. This is critical. This is how we get our density coverage of the total hydration, state of hydration as we drive. On the upper right, we have a mass spectrometer, M-SOLO. This measures between 1 and 100 AMU and provides isotope analysis as well. This is also on continuously, so this will be a really, I think, exciting measurement. As we drive, we'll be able to measure continuously volatiles that are liberated just from the motion of the rover. Bottom left, we have the near-infrared volatile spectrometer system. NIRVIS, this is a system of sensors, but its primary observation is a near-infrared spectrometer that measures between 1.2 and 4 microns. It has a context imager that gives 7 colors from UV to IR and a thermal radiometer for measuring surface temperatures. And then on the far bottom right is our drill. It's a Trident provided by Honeybee Robotics. This is a 1 meter augering, percussive augering drill. It also has 2 temperature sensors, one at the very bottom of at the tip of the bit and one 20 centimeters above that for measuring subsurface temperatures. We also have a heater cartridge in there that allows us to do subsurface thermal conductivity measurements as well. Next slide. We were recently, not too recent anymore, but Astrobotic was selected to deliver us to the moon. That's another interesting aspect of this mission is we are using the commercial lunar payload services program to actually get us to the moon. So a commercial provider is providing the landing services, just like a launch service for us to the moon. Next slide. These are the various Viper mission phases, and it's interesting because if you look at the upper left there, you see the Astrobotic mission. As I mentioned, this is the first commercial, or will be one of the first commercial landed lunar services. Astrobotic owns the mission at that point, just like launch service would own the launch of a satellite. So the first part of the mission, about 10 days, is their delivery of us to the moon. Once we are on the moon, it becomes a NASA mission, the Viper mission. We operate for up to about 100 Earth days, or about 3 lunar days.
You have 5 minutes, Antonio.
Thank you very much. We'll rove in and out, rove between sunlit regions where we hibernate to PSRs to do our studies. Next slide. I'll go through these rather quickly here because I'm short on time. Of course, while driving, we have 3 instruments that are on continuously: the neutron spectrometer, the mass spectrometer, and the nervous near-infrared spectrometer system. That allows us to get as much data over as much area as possible. Next slide. In designated areas, some we choose ahead of time, some we choose based on the data we see in real time. We will drill down to 1 meter in 10 centimeter bites, 10 centimeter segments. Each bite is deposited onto the surface where both the mass spectrometer and the near-infrared spectrometer will make observations. And in each of the ISR's drill sites, we do a temperature pause where we keep the drill in the hole at depth for up to 30 minutes or more to allow for temperature observations of the subsurface. Next slide. So we've been looking at a number of places to go, and some of these places have a lot in common with other places other people are looking. There's a lot of, the criteria we're looking at are shown on the left. Primarily, it's got to have volatiles. We need a range of these ISR environments. Our point of our mission is to map a range of ISR environments, thermal environments. But we also need to be in places where we have significant solar illumination that we can return to and hibernate to survive to the next lunar day. Next slide. I apologize for running through these quickly. This is a reference traverse in the Nobile region. Just for reference, again, we've done many of these traverses. On the right, you have those ISR types that I mentioned. Here, red means PSR, not white. And the line shows the rover traverse through these regions. It's summarized in the upper left there. This was about a 13-kilometer traverse. It shows the number of different ISR types we enter there. Down the bottom, you have the total mapped area. It's quite significant. Next slide. I think that should probably be my second to last. Yeah, this is my last slide, I believe. So where we're at now is planning with ever finer resolution. This is a 1 meter shape from shading DEM that we produce at NASA Ames using NAC imagery. And we're able to use this with our planning tools, hazard maps, et cetera, to plan science stations now and to literally a drive segment at a time. Next slide. I think that's my summary slide, and this is the timeline. So this is where we're at. We have our CDR this October and launch in 2023. And that's it. Thank you.
That's great. Thank you very much, Tony. And just congratulations on getting to this point with Viper. I know it's been quite a journey to get here. So
that's an understatement.
Yeah, so well done. It's really exciting mission. There's sort of one question in the chat was how are the neutrons in the NSS generated?
From galactic rays. So we use nature's abundance of galactic rays interacting with the lunar regolith to generate neutrons which will leak up from about 1 meter deep. The generation of those neutrons are equivalent or better than any active neutron source we would bring with us.
That's great. Thanks very much.
Unlike on Mars, which an atmosphere filters out a lot of.
Yeah. And then one other question from Clive Neal. So what is the launch vehicle for Viper? Is Astrobotic in charge of selecting that, or is NASA providing the launch?
Astrobotic is, and it was just announced actually late last week, I believe. It will go on a SpaceX Falcon Heavy.
Awesome. That's great. So thank you very much, Tony. Thanks for joining us today. Much appreciated. Thanks. A great talk.
Thank you all.